use this. Can you hear me now?
I don't know if I can check it, but okay. Maybe just continue and I'll find it out. I'll find out for you.
Okay. Okay, so this is just like the core of the algorithm. And now I would like to focus on what kind of circuits to sample from. And before that, I would just like to highlight another algorithm that existed in the literature, like before our work. So this is like the basics of Krylov quantum diagonalization, and it works as follows. Suppose if I have access to some initial state, phi reference state, and again, I'm imagining that this state should have good overlap with the ground state. If I can apply time evolution circuits on top of this state, again, this H is the Hamiltonian that I care about. I want to figure out the ground state energy of this H. So if I could do time evolution circuit with different time steps, so J is going from 1 to D, and if I could project H in the subspace of these states, so these phi J's are these phi reference state followed by time evolution circuits. And if I could calculate these quantities, so what is happening here? I'm just like projecting H into phi I and phi J basis. Because these states are non-orthogonal states, I also have to calculate the overlap between them. So if I could calculate these two quantities, then I can solve a generalized eigenvalue problem, as long as I'm looking at, let's say, D 10, 20, or 100. So this dimension is not too large. I can do this diagonalization classically. So this is not our work. This is the prior work that we were following. If you could evaluate these matrix elements, then this is what was shown in theory. If you have a good initial state that has a good overlap with the ground state, and if your gap is not too small, again, like n is number of qubits here, then the number of experiments that you need to do in order to converge to the ground state energy is efficient, which means it's polynomial in number of qubits. Okay, so this was proven in this paper by Ipperly and Linlin's group. And I think 2 years ago, we were trying to implement this approach first. We were like, okay, this algorithm has provable guarantees. It mostly requires, just doing time evolution circuits. Maybe it's good to do on device. But as you look at these quantities, I mean, these are very challenging to estimate on the device, right? First of all, you have to prepare these two different states. You need to like project H. So you have to like look at these overlap for each of the Paulis in H. And then you have to do error mitigation on top. So it was really difficult to like get good signal at scale, where it sort of like, matches with state of the art or maybe you hope to beat classical methods. But we did try it, which was published in Nature Communications. And we tried the Heisenberg model on 2D lattice up to 56 sites. But that's where we sort of felt like, okay, this approach cannot scale because it requires these estimation of matrix elements and a lot of mitigation. But then we were curious, okay, what if I just sample from these time evolved states? Could I now prove that sampling from them, getting bit strings from them, and then finally diagonalizing on an HPC could take me to the right answer? And it turns out that yes, I think that would be sufficient under some assumptions that I'm going to lay out now. So all I'm saying now, you have these states where you started with the phi reference state. Sorry, let me remove this. You start from phi reference state, you apply time evolution circuits. And as I was saying before, I had 3 criteria for making any candidate an advantage candidate. So this sort of satisfies the first criteria because I'm doing time evolution circuits. If H does not have too many terms, then it would lead to shallow depth circuits for my experiments. The next step is I will run these different experiments. So I'll run it for 1 time step, 2 time step, up to D time steps, get samples from all of them. So maybe let's say I took D to be 10 different states. And I took, let's say, 1 million shots from each experiments. So I will have roughly 10 million bit strings with me. So I'll take all these 10 million bit strings and then submit those to an HPC device. So in our case, we were like, doing these quantum experiments, collecting all the bit strings and then sending it over to Oak Ridge over cloud. And then they were just doing everything on their HPC to do the diagonalization. Now, what is our claim? Like, what is it that we have proven in this whole setting? And just to say about the second criteria I had about noise robustness, because we do some configuration recovery and because we are doing subspace diagonalization, these two things gives noise robustness and also some way of mitigating the effect of noise. I'm not going in detail for that, but if we have time, we can discuss that as well. So this sort of checks the second box I had for making anything a candidate for advantage. Okay, so this is what we have proven. If I have a good initial state to start with that has a good overlap with the ground state, if the gap is not too small, and if I imagine that the true ground state can be approximated by a sparse state, and I will define these notions on next slide. But if I have these three assumptions, then what we have proven is that you can converge to the ground state energy with very small additive error with just polynomial number of experiments. So polynomial in number of qubits. So that made me excited early this year because at least even like this for this algorithm where I'm using HPC quite heavily, and also like there is some inherent noise robustness, we could give some provable guarantees as well. And I will describe the experimental results, which will sort of build trust also in these experiments, also in this algorithm. So just to define mathematically what I mean by sparse state. So in principle, I can define a hard cutoff where I say, okay, instead of 2 to the n, I only care about 10,000 bit strings for my problem. Or I can sort of like make it smoother. I can say that, okay, out of 2 to the n bit strings, there are L bit strings where most of my support lies. So this alpha L is a parameter, which is sort of saying that, okay, out of 2 to the n, L bit strings have all the support. And then I also require each of these bit strings up to L to have sufficient weight as well, because that sort of comes in the proof. Because I'm sampling, I'm requiring these bit strings to show up in my experiments, because when I do the diagonalization, as long as these bit strings showed up, a diagonalization will give me the approximation to the ground state supported on these bit strings automatically. By the way, feel free to ask questions if I'm going too fast or okay, so only like this is the next slide is the only scary slide because it has the proof details, but it's easy to read. So all I'm saying here is that suppose phi 0 was my true ground state. So this is the ground state energy. I can approximate the ground state energy up to this additive error. So this is the bound on this additive error. And as you can see, it depends on this sparsity parameter. So if the ground state was really sparse, then you can actually achieve zero energy if you need. And now the question is, okay, how many experiments do I need to do, or how many shots I have to spend in, let's say, on each of the states that I was sort of preparing earlier. So phi reference state followed by time evolution circuits. The answer sort of goes as follows. So suppose I wanted to achieve some epsilon additive error. So let's say if I define to be epsilon, then the number of experiments that I need to do scales like this. Now there are too many parameters, so let's just look at them. So D was the number of Krylov states I use. L is the total number of bit strings that I care about, or like when I was defining the sparsity of the ground state. So L sort of defines the number of bit strings that appear in my sparse representation of the ground state. Gamma 0 is the overlap of the initial state with the true ground state. Beta L was also another sparsity parameter we had. And this epsilon prime or epsilon tilde have dependence on the gap and also the spectral range. So now if you go back to what I was describing earlier, if you just put these information in that formula, that the initial state overlap is 1 over poly n, gap is also not too small, and the ground state is sparse, then you will find that the number of experiments that you need is only polynomial in number of qubits. So this sort of makes the complexity theory people happy because like, okay, asymptotically, everything is polynomial and this algorithm can scale. So before talking about the experiments that we have done, I just want to highlight 3 key properties of this algorithm. There is no false positive. What it means is that we are getting the sample from device, diagonalizing on an HPC. The final output is a well-defined wave function, right? Because I just took 10 million bit strings. I'm representing my wave function in that subspace. It's a well-defined wave function. So the energy of that wave function is a valid energy. So variational principle is satisfied. So you will always have an upper bound on the ground state energy. There are some methods where you can approximate the ground state energy, but you're not guaranteed that it's coming from a state. So there are ways to approximate ground state energy using non-variational ways as well. And as I said, like there is a provable guarantee for specific, like under some specific assumptions, the sparsity of the ground state and also good initial state. And unlike variational methods, where you could imagine that maybe it requires shallow depth circuits, I mean, we don't really need any ansatz. I think only input that you need is to find this good initial state to start with. But that is also a requirement for phase estimation as well. So that requirement will always face anyway. But beyond that, we don't need any ansatz for our algorithm. Okay, so that sort of covers like the theory part of our work, where under these assumptions, we could prove that this method could work. But again, if you go back here, let me just to say that if you go back here and if you really put the numbers for specific values of initial state overlap and the gap, I mean, theory bounds are always loose. So this would just tell you that you have to do maybe trillions of experiments, not millions. So then we wanted to check in practice, if I just stick to millions of experiments, could I get good energies or not? I mean, in order to do experiments, you have to pick a system. And for this algorithm, we picked impurity models. So impurity models are a good test bed for materials calculations. So the reason we picked these is because we were somehow hoping that the sparsity assumption could be satisfied for these models. So we were just looking for models where ground state being sparse in computational basis could give me a sort of good estimation of the ground state energies. So we look at, so even if you don't know about impurity models, it's fine. I think it's just imagine that this is just some Hamiltonian which we sort of lay out on IBM Heron Heavy X device, and we follow the algorithm that I just described. So we look at two different kinds of problems. One is 1 impurity and 41 bath sites. Another one is 4 impurities and 28 bath sites. So this was like an easier experiment in comparison to this. So as you start increasing number of impurities, then the problem becomes challenging for classical methods as well. So we started with this, got good signal, and that sort of like, inspired us to like even try a more difficult system. This is an outdated slide. This is also, you can find on arXiv now, the 4 impurity case. And this is how it looks like on the IBM devices once you lay out these problems. So let's look at the results that we have. So this slide is for the one impurity case. The classical method that we are comparing against is DMRG. So for these models, DMRG is like the state-of-the-art method. And what we are plotting here is the relative error. So SKQD is our algorithm, and we are calculating the relative error with DMRG. On the left, we have the relative error in ground state energy. So these these are like different system parameters in the Hamiltonian. So we try for like different Hamiltonians for one impurity case. And as you can see, and also like on the x-axis, we have the subspace dimension that we are exploring. So the subspace dimension where we are doing the diagonalization on NHPC. So as you can see, even for like different U values or different system parameters in the Hamiltonian and different subspace dimension, we are actually getting quite good relative error to DMRG. Yes.
Just take some details about how big the Hilbert space is for everything that very difficult reference space time.
That's true. Yeah. So let me just have to jump here. Yeah. So this is the size of the Hilbert space if you were really diagonalizing in the subspace where the ground state lies. So maybe I can talk about this slide first. So let's say if I look at some electrons problem or like impurity model problems, I can restrict myself to like some subspace of like some symmetric subspace. So let's say I have 50 electron system. So in principle, I should have bit strings coming out with Hamming weight 50 in my experiments. But then that space could still be gigantic, right? It could still be exponential in number of qubits. So this slide is sort of showing the memory requirement for different problems that people have sort of tackled over the years. So this propane example is the memory that they have done brute force diagonalization. So the ground state energy for propane, they just did brute force diagonalization, and this is the memory that they needed to get to the energy. Then we tried like some chemistry problems, which I'm not describing for now, but for this chemistry problem, the memory requirement to diagonalize in the subspace where the problem lies is this much. And the impurity model that we are trying here, like the memory requirement is like 8 order more than what we were doing for chemistry. So this is just to say that if you just did brute force diagonalization, not doing any algorithm, just, like just take all the possible bit strings that you can and diagonalize, this is the requirement you get from memory, which we cannot solve them by brute force. Okay, so on the left, I hope I have convinced that the relative error is quite good, even for different Hamiltonian parameters and also across different subspace dimensions. On the right, what we were trying to look at is also, not just the ground state energy, but spin-spin correlation functions and density-density correlation functions. And the x-axis is sort of like the distance from the impurity. So this is the case when we have just one impurity and 41 path sites. So this is the distance from the impurity location. And here also, like, relative error is quite good with respect to DMRG. So after we got these results, I mean, obviously, right now I would not say we are, on the cusp of beating classical methods for these problems, but this sort of inspired us to try even a harder model. And at the end of my talk, I will sort of share some new results where we are beating classical methods. So this is sort of like the chronology of ideas and then results that we got, and that sort of made us excited to try, some advantage candidates. So this is for 4 impurities case. This is again relative error. Remember at the HPC component, I did not describe very carefully. I just said that we give bit strings to either Fugaku in Japan or Oak Ridge National Lab, and then they do something on it. That goes through like many steps. We do some flipping on noisy bit strings, and we do diagonalization, and then we repeat that procedure. So this is for 4 impurity case, where all I'm trying to show here is that the procedure that we follow on the HPC side, even though it's heuristic, but with very few iterations, we actually converge to the state-of-the-art solutions. So on the this dashed line and the solid line, this is the state-of-the-art. So this SCI is again some selected configuration method which requires powers of H. And if you don't know DMRG is nothing but it's just a variational method where you are optimizing over MPS representation of ground state. So we sort of match with these 2 methods for 4 impurities case as well. And this sort of builds, I mean, through this procedure, you sort of build some trust in the procedure as well, right? So we do something on HPC side, some flipping based on some distribution that we have defined. But that procedure actually at least converges to the right answer. The right side of the part, I think it requires more time to explain, but I also just want to emphasize, I think so far in my talk, I've been saying sparsity in the computational basis, and you should question that, because why would a ground state be sparse in the computational basis to begin with? We can go beyond those assumptions in the post-processing. So the right-hand side, you see here orbital optimization cycle. So let me just define it in simple words. So suppose I got the bit strings from the device, I did the diagonalization, and I have some approximation of the ground state. Now what I can do is I can apply some basis transformation over the Hamiltonian. So I can just do U dagger, which is parametrized. And I can ask, okay, can I find a unitary transformation so that the energy of the ground state that I got sort of goes down with that unitary transformation? What kind of unitary transformation to choose? How can you keep it classically efficient? How can you do everything classically in the post-processing? Those are the questions that we can discuss afterwards. But we do such a thing for these impurity models, and we could at least push the error from 10 to the minus 2 to 10 to the minus 7 by doing this transformation. So at this point, if you ask me, is it sparse in the computational basis? Answer is no. It actually became, now the ground state is sort of represented in a basis, which is, let's say, coming out of even linear depth circuits. So I can define some basis by applying some unity transformation, and it's actually sparse in that basis now. So this is how we go beyond the ground computational basis sparsity. But actually, there are more open questions, which I'll be happy to discuss. Is, let's say, given a Hamiltonian, what basis should I sample in? Can I just, from the get-go, I just like sample in a good basis instead of computational basis? So I can apply time evolution circuits and then sample in that given basis that is informed by the problem. And then I diagonalize in that bit string subspace. So when I say bit string, is bit string in that particular basis subspace. So those are the open questions that we are trying to study for now. And it's not clear. I think, at least from theory point of view, it's not clear how to answer it. So we're just like looking at some heuristic approaches to learn that. Yeah.
The original basis, for example, orbital, where we just compare this again.
Yes, here it's natural orbitals. Yes. Yeah. Yeah. And then we do further optimization. Yeah, that's correct. Yeah, I think maybe just to like give an example where basis plays a role. Let's say if my Hamiltonian was, let's say, sum of, let's say, negative sigma x, sum over all the qubits. My ground state is all plus states, right? Like tensor product of plus states. If I gave you that ground state on the device, and if I just sample in the computational basis, I will never reach to the energy. Whereas if I was sampling in the Hadamard basis, I'll quickly converge to the energy. So that's why like the basis choice is really important for a given Hamiltonian. So far, I sort of like, I hope you at least partially agree that there is some provable guarantees, and then we could also like build trust in the experiments. That was like the one particular algorithm that we studied this year. But before that, we had something called SQD, which is just sample-based quantum diagonalization. There is no Krylov part in it. So this was done for chemistry. This was very heuristic. There was no proofs. But there also we could get good convergence to the answer, let's say matching with classical state of the art up to like 70 qubits. I just want to say maybe I should go back and say why. Yeah. So even though this algorithm is nice, I cannot really apply it to chemistry still, because number of terms in Hamiltonian for chemistry Hamiltonian is like order millions. If I again try to do traumatization for a Hamiltonian that has millions of terms, the depth requirement will be crazy. So this algorithm is suitable for lattice Hamiltonians where number of terms are not too crazy. But we really wanted to like come up with a method where we can apply such an approach for chemistry as well. And that sort of led to our new results maybe like a couple of months ago, which is sort of like the randomized version of what I described today. So you can imagine, let's say if I have way too many terms, then I cannot really do traumatization with respect to all the terms. But what I can do, I can just like do importance sampling based on the coefficients, and then just apply. So let's say if my budget is 100 depth circuit, I will just like sample a term based on the absolute value of the coefficients here. And then whatever it spits out, I'll apply that gate. And I keep on applying gates until I hit the 100 depth mark. And then I can just sample from those circuits and do the diagonalization on HPC. This also we have tested on some molecules so far, but we are still pushing it to the limit, where we can be excited about sharing with everyone. So this is our new efforts for applying this algorithm that I described for chemistry problems. I've already discussed this slide. So now the next question is like, how do we get to advantage, right? That's so far I was excited to share like the provable guarantees, some trust in the devices. First of all, like we pushed the experiments to like 70, 80 qubits and could get signal such that we match with state of the art. I think I would not have predicted even a year ago, because that's because you can ask this question, okay, what if I do this procedure by just like randomly sampling bit strings in the subspace that I care about, and then just apply the same procedure? You do not reach to the answer. So that's sort of implying that there is signal on the device. We are getting some signal, and then obviously we are improving the noisy signal as well by doing some post-processing on the HPC side. This is the scenario, right? Like we have some The true ground state is maybe far away from what we are pursuing, but as long as we can fall in this region, that would be really cool. The first thing is that the three criteria that I had about, shallow depth circuits, provable guarantees and trust in experiments, and then inherent noise robustness and mitigation capabilities, like all those boxes are checked out now. So at least we can imagine that maybe there exists a Hamiltonian for which this algorithm will outperform other classical methods. So that's the approach we took. So let me skip this. So I will share the final results, like the latest results that are now not out there. But let me just conclude by saying this quantum-centric supercomputing, like this whole framework that you might be hearing at different workshops, I think it's a good test bed for current quantum processors where we can pursue these ground state algorithms, which was not possible before. I think prior to what we were doing, I think we were exploring maybe 20 qubit problems. Now we can stretch it to 80 qubits. These experiments are sort of building trust in these algorithms, and also we are showcasing that we are able to get signal from the device. And no false positive, I think that's like a good property to have. And then we have provable guarantees. And before talking about the latest results, I also want to highlight that we have these tools also added in Qiskit where, like the whole setup that I described, you can also just use it right away. So you can just give a Hamiltonian, say that, hey, run this algorithm. This add-on will automatically take care of it. It will apply time evolution circuits on the device, and you can diagonalize on HPC, on an HPC after that. So this add-on is quite useful. I mean, I'm using it quite actively. And the another thing that we have sort of introduced recently is this quantum advantage tracker. So what we are really hoping is that, we did these experiments for ground state problems. And then we also have experiments for expectation value problems, like time evolution circuits, and then expectation values, and also like peak circuit problems that I was describing. We have just put those circuits on GitHub, and anyone can play with those. They can try whatever classical methods they want on those problems. And our hope is that I think community can sort of, put new problems that they are trying on quantum hardware. And then anyone with their classical expertise can try their method on those problems. So far, Flatiron Institute, an algorithmic company, and obviously Oak Ridge and Riken, like they have sort of put their classical methods for these problems. And I personally like it better than research papers because at least here you can just query the circuits directly and then use it for your classical algorithms or quantum hardware. I think it would be cool. Let's say if IBM does some experiment, then Quantinuum runs similar experiment on their hardware, and then they report their numbers. So it will be like a good table to have, moving forward. And I think I'm hoping that we'll see more and more experiments being done at advantage scale. And maybe community can decide which experiment is achieving advantage instead of any company claiming for it. Okay, so let me share how we are approaching the problem now. So remember, we had these three assumptions. So now I can sort of start from a different problem. I can say, okay, maybe I don't look at physical Hamiltonians. I just want to come up with a Hamiltonian where all these assumptions are satisfied. So a local Hamiltonian such that the initial state has good overlap with the ground state, such that the gap is not too small, and the true ground state is also sparse in the computational basis. So I will start with these assumptions and I'll construct a local Hamiltonian. How do we do it? Like that I will share once the paper is out, but we have a machinery to construct Hamiltonians which satisfies these assumptions. And then once we constructed those Hamiltonians, I mean, obviously that required a lot of tweaking, a lot of tests, but now we have some instances of local Hamiltonians where our approach, when we ran on quantum hardware and then did HPC diagonalization, achieved lower energy than the SCI methods. Remember the power methods of H, like applying powers of H on initial bit string? It achieves lower energy than those methods when, let's say, you're looking at the same subspace dimension. So this was not happening for all the cases that I described before for impurity models. Like we were outperformed by classical methods and we were just saying that, hey, we are converging to those solutions. But now I'm sort of spinning the problem. I'm saying that, okay, I don't care about physical Hamiltonians for now. I just want to find a Hamiltonian for which our approach outperforms classical methods. And we have constructed such Hamiltonians. And this is like one example of that, where given a fixed subspace dimension, quantum approach is producing lower energy than classical methods. So now, I mean, I'm obviously like changing the game now, right? I'm saying, okay, I'm describing advantage now by saying I achieve lower energy for the same subspace dimension. We did not push quantum approach to this point for now. We are testing that. So what is really happening here is that those classical methods, when I increase the subspace dimension, they end up actually producing lower energy than quantum approach. So right now, what is being tested is like to push for larger subspace dimension for the quantum approach as well. But at least this is giving, first signature for advantage when I'm, let's say, just setting like a fixed subspace dimension and asking for lower energy. So the reason is simply because I mean both are approximation methods, and somehow quantum is able to give you the right set of bit strings that matter to your ground states. There is no no. So the what is given to both algorithms is same set of information. So I described the local Hamiltonian in terms of Pauli's, and I gave them the good bit string to start with, which has a good overlap. So I'm giving that promise as well to both methods. And then after that, both approaches try different things. So classical approach applies powers of H. Quantum approach applies time evolution circuits. And then both approaches diagonalize in the subspace. Which subspace you diagonalize in? So on the classical side, that's chosen by perturbation theory. And then on our side, we just get all the samples that we get from the device and then diagonalize on an HPC.
So is this like ED, but the subspace dimension
Mm-hmm.
we see the subspace dimension that we're searching.
Yeah, so it is well defined from the proof, right? So this, if I give you the promise that the true ground state could be well approximated by a sparse wave function, then the number of experiments that you need, sorry, I have to go back. Number of experiments that you need from each Krylov states scales like this with system parameters. So all the information that you care about, initial state overlap, gap, spectral range, number of Krylov states, all appear in this formula. And all it's saying asymptotically is that if these conditions are satisfied, then you only need polynomial number of shots from quantum device and just diagonalize in that subspace. And then you're good to go. And I think I would like to emphasize here that even if I give same assumptions to a classical algorithm, there is no provable guarantee. So we have tried proving it for the power methods as well, and we don't have any proof so far. But this is we could only prove it for a quantum approach. I think with that I can stop, and maybe other things I can discuss after my talk is over. Yeah.
Thank you so much. Any questions? So this is the time for questions. Yes, go ahead.
So sorry, for which one? Oh, the last one. Yeah. So yeah, I sort of the proof sort of goes through easily, like for this algorithm as well. Because if you are familiar with like Q-drift, the original Q-drift paper, okay. Yeah, so the short answer is that, yeah, we have provable guarantees, like similar to what we have for the middle box, like SKQD, same guarantees apply to this algorithm as well. But again, the issue is that when you try to put in numbers there, like the depth will be quite a lot, like not 100 depth circuits. But this is how proofs usually go, right? Like proofs are like quite loose, and then you just do the experiments to see if you get the signal with less depth circuits. Sorry, can you speak louder? Yeah. Yes. So though there also it's the same argument that there I have some magical way to like find good bit strings. I have some set of rules to find those. But then once I've found those bit strings, I diagonalize my Hamiltonian. So at the end of the day, it will be a wave function supported on 10 million bit strings, let's say. Yeah. Yes. Right, right. Yeah. So we also, yeah. So for those classical methods, we also give them freedom to try whatever they want. Yeah. Usually it's better, even for them, I think it's better to start with the input that we give. Maybe I did not say this, but for the nice plot that I was showing for making a case for advantage, if you run DMRG for this, DMRG cracks it. So DMRG is still, like the beast that we have to beat. And I think the argument in favor of DMRG for what we are trying right now is that because we are looking at some sparse representation of the ground state, maybe that can be well approximated by an MPS, right? Then the question is like, could you find such a representation? Like, I mean, DMRG is supposed to work for 1D Hamiltonians quite well. We are throwing these problems for 2D Hamiltonians. We have some instances where DMRG is also struggling, but running them on the device is a challenge right now because of the depth requirement. Yeah.
I have a stupid question, I think. The conditions that you say where you have these guarantees if you meet these, yes. It just seems to me that since you're trying to find the ground state, how do you know that you, for example, have good overlap with the ground?
Yeah. So right. So the problem that I described here I know everything about the ground state because I'm just artificially constructing it. So my hope is that I'm constructing it. I know how to construct it. I'm not telling you, and I'm also not telling it to the quantum algorithm either. What I'm giving is the Hamiltonian and then the initial state.
I mean, an exam, you already know the answer.
Yes.
So real world problem might not be simple to know if you meet them.
That's correct. Yeah. So so I think so we tried it for some real world problems, let's say chemistry, impurity models, where we could say that okay, we are matching with state of the art. Now the question is like, could we use this algorithm and then beat classical method for some real world problem? I think that's up to the like test on the devices. So you just try. And also like these assumptions I needed for the proof. It could be that maybe these assumptions are not satisfied and still I can get better energies than especially the sparsity assumption that I'm saying that I just need for the proof. It could be that I still do better than classical methods. So the bar is lower than what I would sort of set for fault tolerant devices. Right now, I just want to beat classical methods and not care about, predicting reaction rates or something useful. Yeah. Yeah. That's correct. Yeah. Yeah, you could say that. Yes, you could say that. I mean, I think even I think at the core, how I think about this is that, when I apply powers of H, and because I have to discard some bit strings, just because, I cannot tolerate the memory of all the bit strings. Whereas if I do time evolution circuits for different time steps, somehow like the superposition and like constructive and destructive inference, automatically removing the bad bit strings. Like I don't see them when I sample. So instead of like, like just truncating the memory or truncating the bit string subspace because of the memory issues, somehow the time evolution circuits is taking care of it. And I don't have to like remove them by hand. And that's why you could imagine that it is more powerful than power method.
I think one question
Yeah.
would have to pull that.
Oh, is it in the chat?
No, this actually someone, Soham, I think, I don't know if we can hear you real quick, maybe try it.
Okay,
Yeah.
can you hear me? Yeah, so my question was that you mentioned that you're also computing the spin correlation. So
Yeah.
I was wondering, uh, how are you doing that with this particular with KQD or SKQD type?
Oh, yeah. I mean, that is again like simple, right? So at the end of the day, we get some approximation to the wave function, right? So we just get a wave function on an HPC. Now
Okay,
I can query any operator
I
observable.
see.
Yeah.
I see. So you're doing that after you have got the wave function
Exactly.
on the IPs. Okay, thanks.
Okay, great. So then any last question? No. So then let's thank Kunal real quick.